In this session, we are going to discuss a graph-based shortest path problem. In our previous sessions, we had talked about the graph data structure, and we also discussed how to perform the graph traversals in BFS and DFS algorithm, and we also implemented those algorithms in a Java program. So now we will shift our focus to this shortest path problem in a graph. First, we will define this problem, and then we will look at some existing solution to this problem. And we will pick one such solution in Dijkstra's algorithm, and then we will talk about how to solve the problem using Dijkstra's algorithm. And at that point, we will also do a time complexity analysis on the algorithm. And later, we will take up a class activity to practice that algorithm. So firstly, let us look at the problem itself, and let's formally define the problem. So we are given with a starting node S, which is the source vertex. And then we are also given with a weighted graph G, where we have capital V is the node set or the vertices set, capital E stands for the edge set, and capital W is the weight of all the edges, Cij, where the edge is from I to J. So basically, it is a weighted graph. So the problem is, if we are given with such a weighted graph and the source vertex or the starting vertex S, we want to find the shortest path from node S to all other nodes in the graph. So it's a one-to-all shortest path problem, right? So we are given with one vertex, and then we want to find the shortest path to all other vertices in that graph. So this shortest path problem has several solutions which are proposed in the existing repository of algorithms for CS. One such algorithm, the popular one, is the Dijkstra's algorithm, where we are given with the graph and we are trying to find the one-to-all shortest path. And we should keep in mind this algorithm works for non-negative cost of edges, meaning we need to assume that the edge weight is greater than or equal to 0 for all the edges in capital E. And then the second algorithm is the Bellman-Ford algorithm, which is the algorithm that is applicable to problems with arbitrary cost, right? So it doesn't need to be fixed to non-negative cost. It could be negative cost as well. And Floyd-Warshall algorithm is also working with arbitrary cost, and more generally, it works for all-to-all shortest path algorithm, right? Meaning from any vertex, we could find the shortest path to all other vertices, right? So it's an all-to-all shortest path problem. And finally, we should point out that Floyd-Warshall and Bellman-Ford algorithm solve this problem in graphs that do not have a cycle with negative cost. For simplicity here and for time's sake, we are going to discuss only the Dijkstra's algorithm, but the other two algorithms is also good to spend some time by ourselves to look at how those algorithms are implemented. So let us shift our focus to the Dijkstra's algorithm. Let's look at what's the power of this algorithm initially, some advantages and applications of this particular algorithm. One such application is the maps, such as Google Maps or MapQuest. If we consider each node as a city, let us say we draw a graph like this, right? So I have a graph like this here, and I am, let us assume that this is a graph in Pennsylvania, and then you have the cities here. Let's say Philly, Harrisburg, and then you have Pittsburgh, so on and so forth. Let's take some random cities there in PA. And at any point here, we could find that a shortest distance from Philly, let's say to Pittsburgh, the Dijkstra's algorithm would be able to provide us, because we have an edge weight here, and each edge weight we're assuming that it could be the distance in miles, if we would consider it that way. Then we could simply apply the Dijkstra's algorithm to find the shortest path from Philly to Pittsburgh in this case, right? So that's one such application. And there are several applications in this domain here. And let's look at a few more. The other application would be the network, where the data packets are sent in a data network routing. So we could find the path for the data packet to go through such a network with a minimum delay. And then the same thing could be used in robotics, transportation, and VLSI design, where we make circuits, right? So clearly, every time we have a graph-based problem and we would like to find the shortest path from one vertex to all other vertices, we should be able to do so by applying the Dijkstra's algorithm. So let us now look at the example for Dijkstra's algorithm, and then we will, at that point, we will also look at the pseudocode of the algorithm. So let's say that we are given with this graph G. In this case, it's an undirected weighted graph. And let's keep in mind the algorithm would also work for a directed graph as well. But here we are just considering an undirected graph, a weighted graph here. And we like to start from the vertex 0. And we want to know the shortest path from that vertex 0 to all other vertices. So first thing first is we need to construct two arrays. One is the distance array and the other one is the previous array. And distance array would tell us at any point of time the distance from the source vertex, in this case 0. And the previous one would tell where did we come from to that particular node, right? So we know that we start from 0, but what is the node that's previously visited? We need to keep track of that so we can build a path. If we want to build a path, a shortest path, then we need to keep track of the previous nodes. Okay, so we need to initialize this, both these array. Distance array would be initialized the first, or the in this case the source vertex that we are taking from the input of that algorithm. In this case, we are assuming that the source vertex is 0, so we simply set that as 0, and all other vertices would be set to be infinity. And infinity is just a theoretical notation, but then if we want to do it programmatically, we would need to do an integer dot max value. Right? So we would need to find the maximum value in any programming language. Let's say in Java, you want to find the maximum value for integer and assign it there for all the vertices initially. And then previous here, we are assigning it a negative weight, negative minus 1 to start with. We're just initializing it that way. And then we will proceed further from here. So let's say that first thing first is we are taking the node 0. And we are going to look at all the unvisited neighbors of node 0. And we compare that with the previous distance that we already have for those vertices. So now for 0, we know that we have to consider 1. And we need to consider 3. We need to consider 4. Right? So those are the 3 unvisited neighbors for node 0. And then you can see that we update the distance, and the distance is updated basically based on the distance of that particular node, which in this case is 0, plus the edge weight, right? So now you can see the distance of 0 was 0. 0 plus 3 is going to be 3. 0 plus 7 is going to be 7. 0 plus 8 is going to be 8 for the distance of 4, right? And you should keep in mind that the original distance was infinity for all the 3 vertices. So any number would be lesser than infinity, right? So we'll simply update that 3, 7, and 8, right? So that's the value that we are updating. And we should keep in mind every time the algorithm is picking the vertex with the minimum distance, right? So in this case, alpha, let's assume that the minimum vertex with the minimum distance is alpha. So here alpha was 0 to start with. And the next time we are going to set alpha is equal to 3, because the 3 is the minimum distance, right? So in this case, let me make a correction. Alpha is equal to 1 because alpha is always the vertex, right? It's not the distance, it's the vertex with the minimum distance, right? Vertex with the minimum distance. So here you could see that the vertices are 0, 1, 2, 3, 4. So we are picking 3, and thereby the vertex that correlates with the distance 3 is the alpha. So alpha is equal to 1, right? And then we are going to, at that point, we will simply look at all the neighbors of 1. So basically we have 3 neighbors, but we are looking at only the unvisited neighbors, right? So this is why I don't need to consider 0, because we already considered that, right? And then look at this particular edge here between 1 to 3, right? So 1 to 3 is already to visit 1. We took a distance of 3, and then 3 plus 4, this is nothing but 3 plus 4 right here, is equal to 7. And that 7 is not lesser than what we already have here. So we just leave that alone. But look at 2, right? So look at the vertex 2. There's an edge between 1 and 2. And this is going to be 1, the edge weight. So simply we need to add 3 plus 1, which is 4, right? And why are we adding 3? Because 3 is the distance of that particular vertex 1. So we are adding 3 plus that edge weight 1, which is 4. And clearly 4 is lesser than infinity, right? So this was the previous distance. So we need to update that because it's lesser. So we are going to update 4. And then we are also going to set the previous here as 0, right? So previous is always set as 0 in this case, because we are coming from that particular vertex here is 0, right? So we came from there, and we are going to update the previous for 1 as 0, right? And then we make that 1 as visited at this point, and then we move on to the next node, right? So what would be the next node here? We have done with 0, 3, meaning we are done with node 0 and 1. And now we need to pick the minimum 1 from the other unvisited vertices. So clearly we will pick 2 because it has a distance 4. We said alpha is equal to 2, right? And then we are going to look at alpha equal to 2, which is right here. And then we are going to look at all its neighbors. Neighbor or 3 and 1. 1, we don't need to take that into consideration because simply we had already visited that particular node. And 3, we have a edge weight 2. And to come to 2, we had taken a distance of 4. So 4 plus 2 is equal to 6, and that's better than 7. You see, in the previous distance, we have 7 there to visit the node 3. And basically, we were saying that, hey, I will take the edge from 0 to 3, and that cost me 7. But then later we recognize that if we would do 0 to 1, and then 1 to 2, which is 4, and then 2 to 3, which is 6. That's a better route, right? So that's the shorter route, I should say. And that is why we are going to update that as 6 here, as you can see. So the update is done to be 6. And then we will proceed further from there. And now we are going to simply, at this point, we are going to take the next node in that sequence, which is again the shortest node. We are going to take the shortest node, and then it will get the shortest node as 3. So we were visiting 3, and we are looking at the neighbors of 3 here. So you could see the neighbor of 3 is 4 and 0. 0 is already visited. So 4 is the neighbor that's unvisited, and the edge weight for 4 is 3. And keep in mind, we have distance 6 for that particular node 3. So 6 plus 3 is 9. It's not lesser than the previous weight. The previous weight was 8, right? So the previous distance is 8. So basically we don't update that. We just keep the 8 as it is, right? And we are saying that at that point, hey, I came to the node 4 from 0, so which is this one, 0 to 4. That's better than any other route, right? So we are saying that 0 is the previous one. And for the node 3, as you know, we took the route 0 to 1, 1 to 2, 2 to 3, right? So we need to update the previous as 2, right? So previous was 2 for the node 2. Okay, so that's the idea here, is then we go to the last node, node 4, which is the distance 8. And we look at the neighbor of node 4, 0 and 3. Both of them are visited. We simply get rid of that particular item, right? So there's no more item to look at because we had visited all the vertices, right? And we had come up with the distance array and previous array. And simply if we look at the previous array, like for example, if we want to look at 0, 1, 2, 3. Let's say we want to look at node 3. And you can look at the previous node, which is 2. Then 2 here simply means we need to go to 2. So we go to 2 and we look at 1. Then we go to 1. We look at 0, right? So then the path here is simply 0 to 1 to 2. Right, so that's the path, and then you know that 2 to 3 is the path that we had taken to visit 3. Right, so using the previous node at any point of time, one could build the path here, the shortest path, and the distance will provide us the distance of that particular route, right? The total distance. And that would be the minimum distance, or the shortest path, the distance that we had covered so far. Okay, so with that understanding, let's go and review the algorithm here. The algorithm takes in the input graph G, either directed or undirected, but it got to be a weighted graph because we're trying to find the shortest path. And the output is shortest distance from S to all other vertices in V. So initially we set the D of S as the distance of S here. D here stands for the distance array, right? Distance array. And P here stands for the previous array. So we set distance of t equal to infinity for all other vertices, v minus s, which means excluding s, because s is the start vertex, right? So we exclude that from all other vertices, and we set that to be infinity for all the vertices t. And then p of t will be undefined. Undefined here, we are saying that we could set that as -1 for all the vertices of t element of capital V. And then we run a while loop. While visited.size is not equal to the total number of vertices, which is the cardinality of V. So this simply means total number of vertices, right? Total number of vertices. And then we're going to check if there is an unvisited vertex, then we find the minimum distance in that unvisited vertex, right? So we find all the vertices, unvisited vertices, and we find the vertex with a minimum distance, and we set that as alpha. And then we go and explore all the unvisited neighbor of alpha, right? So we are going to find the beta there. The beta here is going to be distance of alpha plus the edge weight between alpha and u, right? And then we check if beta is lesser than distance of u, then distance of u would be updated, and then previous of u would be set to be alpha, right? So previous of u would be set to be alpha, and then we end if, and later we are going to add that vertices here, in this case alpha, we add that to the visited, right? So we'll go back and we will look at this particular case here. I'm going to erase this little bit, right? So let's look at this particular case. So here you could see that we had picked 3, right? So we picked 3, and clearly, when we picked 3, then we would have looked at the neighbor 0 and 4, right? So 0 is already visited, 4 is 3. So to come to 3, we already took 6 as the distance weight. So 6 plus 3 is 9. And you could see that we are updating this to be alpha here, right? So alpha is going to be 2. And keep in mind, alpha was 2 in the previous iteration. If you can go back and look at this particular entry here, alpha was updated to be 2 because alpha was 2 in that particular iteration. In this iteration, alpha was 3, right? But we never picked the minimum one. If the minimum one is picked, only then we will update the value here for previous, right? Previous equal to alpha is done only if we pick the minimum one, right? Okay, so let us talk about the analysis of this algorithm. So clearly you could see that if we can erase this little bit, all these notes, so we can go back to our original algorithm. So one thing to note is that this outer while right here is going to run for all the vertices, which is the total runtime of capital V, right? So V here is the total number of vertices. Is going to run a total number of vertices here, capital V. And then look at this particular line. We want to pick an unvisited vertex with a minimum distance. So in order to find a minimum one, in the worst case, it's going to take big of V as well, right? Because we need to go through all the vertex in the graph and we need to find the minimum one. So that's being done inside the while loop. So it's going to be V times V is V squared, right? So again, let me repeat myself. Outer while is going to go and add all the vertices to the visited, right? So visited array, and then that's going to be V times, and then inside that while loop we would need to find the minimum the vertex with the minimum distance. And in order to find that, it is going to take at least v times, right? So the worst case is going to be big O of v, and thereby the running time is big O of v squared. So we will take our tryout activity for today. Given this graph G, we would need to find the shortest path from all the vertices starting from vertex A, right? So it's a one-to-all shortest path problem. Clearly we can see that from vertex A, we want to find the shortest path to all other vertices B, C, D, E, and F. We need to find all the shortest path here, right? So please make sure you post your solution in our general channel to get the class participation credit before the deadline. And the next step is we are going to talk about minimum spanning tree. Most likely we will start this discussion next week. We will cover Prim's and Kruskal's algorithm. We will talk about MST and also those two individual algorithms to understand how the MST works. There's a reading assignment for today based on our discussion, Sedgwick 4.04. And if there are any questions, please feel free to ask me in Slack or during the virtual office hours. Okay, so thanks for watching this video.